Chapter 7 is where we talked about sampling distributions. And I am in the yellow packet right now. We talked about parameters and statistics. A parameter is a number that describes a population. We use a statistic to estimate an unknown parameter. Sampling distributions describe all values of a statistic in all possible samples of the same size. So a sampling distribution would say if I have a population of 10 and I want samples of size 3, the sampling distribution would be every possible grouping of 3 that you could possibly make in that sample of 10, or sorry, in that population of 10. And then the statistics that you would calculate from all of those different samples. So when we are talking proportions, sampling distributions for proportions, the mean of p hat is your sample proportion. The mean of p hat is the same thing as p, which is the population proportion. The standard deviation of p hat is the square root of p times 1 minus p over n. It's been a minute since we used that formula. And we are good to use that formula as long as what condition has been met? 10% condition, right here. The population is at least 10 times the sample. As long as our 10% condition has been met, we are good to use that standard deviation formula. The shape is going to be approximately normal as long as n times p is greater than 10 and n times 1 minus p is greater than 10. This is our large counts condition. We normally have another condition that we're looking at here. What's the other one that we typically go after? Yes, random sample, so that we can generalize to the population. The shape, we talked about the shape being approximately normal. Then we get down into the bottom. This is talking about means or averages. The sample mean the mean of x bar, the mean of the sample mean, is the same thing as the population mean. And the standard deviation of the sample mean is equal to the population standard deviation divided by the square root of n. As long as we have our 10% condition met. We will be approximately normal if the population distribution is normal, if n is greater than 30, that's large sample, or if the sample distribution is not strongly skewed or has no outliers. And then we will assume normality in the population. But we have to have some evidence for it. If we're going to assume that the population is normally distributed, then we have to be able to point to our evidence and say, well, our sample didn't have any outliers or strong skew, so we're going to assume that the same is true for our population. Does this feel familiar? Hopefully it's the proportions that feels a little bit rustier than the sample means. But we've talked about how to meet our normality condition, how to meet our 10% condition. We haven't talked about the random condition right here, but we get into that with confidence intervals and significance tests. When we are interpreting the standard deviation of the sample proportion of whatever our success context is typically varies by whatever the standard deviation of the sample proportion is from the true proportion of P. So the sample proportion of students that did their AP Stats homework last night typically varies by 0.12 from the true proportion of 0.73. And then there's an interpretation here for standard deviation of sample means, which is interpreted in a very similar way. I would like to look at some examples on the white paper. So this starts with example number 11. If you've noticed the printouts that I've had for the past 3 days, the example numbers just keep numbering from there. That's why we're not starting back at 1. Every Saturday, the Full Deck Music Store has a Draw Your Card Day. A customer may choose to draw a card from a standard deck and buy a second CD for an amount in dollars equal to the value on the card, with face cards counting as 10. For example, if a customer draws a 3, his second CD would cost only $3. If a customer draws a Jack, the CD will cost $10. Let X represent the amount paid for a second CD on Draw Card Day. The expected value of X is $6.50. What are they telling us right here? The mean, yes. Expected value of X is $6.50. And the standard deviation of X is $3.10. So that's our sigma. If a customer draws a card and buys a second CD every Saturday for 10 consecutive weeks, what is the total amount that the customer would expect to pay for these second CDs? So what is the mean for X bar? Does this every week for 10 weeks. How would I calculate the expected value for this? Super close, except I want to look not just at what's the average of what they would spend over those 10 weeks. I want to know grand total, what would we expect that they've spent in 10 weeks? 65. 10 times our mean. So 10 times 650, we get 65. If a customer draws a card and buys a second CD every Saturday for 25 consecutive weeks, what is the approximate probability that the total amount spent for these second CDs will exceed $168? Notice we're not talking about just the average paid each week. We want the total amount. We have to make an assumption right at the beginning if we're going to move forward with this. How many weeks are we sampling? 25. Is that enough to meet our central limit theorem condition? No. Do we have a dot plot of the data? No, so we're going to have to proceed with caution. We're going to assume normality here, but we have to proceed with caution. All right. So I'm going to draw my normal curve. What is the expected total spent on average over these 25 weeks? How would I calculate that? I want to know what the mean is. Yes, 25 times 650. Absolutely. So the mean for our sampling distribution is the number of weeks, 25, times our mean of 650. Which comes out to be what? 162, you said how much? 0.5, so 162.50. That's what goes straight down the center here. And what other information do I need if we're going to do a normal calculation here? I need the standard deviation. So we need sigma of x bar. I know what the standard deviation is for 1 from the population, right? What is the standard deviation for 1 CD from this population? 310. So if we were to do this for 25 weeks, how would I calculate that standard deviation? Yep, 25 times 310, 25 times my standard deviation. But this 25 weeks is a sample, so we have to do this over the square root of n. So over the square root of 25. Go ahead and calculate that for me. What do we get? You said what? 1.55? I got 15.5. So 1550 would be the standard deviation for the sum of this sample of 25 weeks. All right, so we want to determine the probability that in this 25 weeks, the total amount paid for the second CD would exceed $168. So I'm going to put 168 on my graph, and I'm going to shade this to the right. And then how will we calculate that probability? What'd you say? Normal CDF, yes. Probability that x is greater than 168 is equal to normal CDF. What's our lower boundary? 168. Upper boundary? Something large, so I'm going to do several 9s here. 99,999. Then what? mean and standard deviation. So 162.5 and 15.5. Make sure that you are going in and labeling those pieces. You don't just have normal CDF in the parentheses written down. You have them labeled lower bound, upper bound, mean, and standard deviation. Yes? So when we do normal CDF, we have the ability to determine which tail we're looking at. We can't do that with binomial or geometric. It always just gives us the left tail. So with binomial and geometric, if we want a greater than, we want a right tail, then we have to do 1 minus. But because we can put in the lower and the upper boundaries, and we can give it an upper boundary that's enormous, we can get the greater thans without having to do the complement. That's a great question. If you were doing this using table A, so calculating a z-score and then looking up the area in table A, then you would have to use the complement for a greater than. What is our probability? 0.3614. Nicely done. On the next one, example 12. First thing I want to do is check our conditions, and then I want you guys to calculate that, and I'll give you a couple minutes to do so. A plane used to fly tourists in and out of the rainforest contains seating for 16 passengers. The total weight limit for the passengers is 2,500 pounds. Assume the average weight of tourists is 150 pounds and the standard deviation is 27 pounds, and that the distribution of tourist weights is approximately normal. If the weight limit is exceeded, the plane has difficulty taking off safely. We're basically talking about crashing into very tall trees here. Not usually considered a vacation highlight. If a random sample of 16 tourists has booked a flight, what is the chance that the weight limit will be exceeded? So let's check our conditions first. What's our first condition? Random. Do we get the random condition? Yes. Where does it say? Yes. Random sample of 16 tourists right here. All right. What other conditions do we need to check? 10%. So our sample number, 16, is less than or equal to what? 10% of all tourists, yes. And finally, what else do we have to check? Normality, large sample. Do we get normality? Yes, where? Is it central limit theorem? Yeah, it says over here, the distribution of tourist weights is approximately normal. All right. I'm going to let you guys finish this problem. Keep in mind this is for a total weight, so this is similar to the problem that we were just looking at with the CDs where we had a total amount of money. So go ahead and finish this one off. I'm going to give you about 2-3 minutes to do this one. calculate the probability that the plane will not be able to take off. All right. What do we need to calculate before we can even answer the question? Mean and standard deviation. You're welcome. So the mean for X bar would be what? 2,400. How did you get that? You're absolutely right. How did we get 2,400? Yes, 16 people times the mean weight of the tourists. So that would be 16 times 150, which comes out to be 2,400. So that's what goes right down the center and goes next to the N. Then we need the standard deviation. How are we going to calculate the standard deviation of the sampling distribution? Yes, 16 times the standard deviation divided by the square root of 16. So I would have 16 times, what was that, 27? Over 4. This comes out to be what? 108. All right. So there's my graph with the correct standard deviation and mean on it. We want to know the probability that we exceed 2,500 pounds. So the probability that X is greater than 2,500 is equal to, how do I do this? normal CDF. And then what? Lower bound, so 2,500. Something large. Because 2,500, or 2,400 rather, is my mean, I want to make sure that my upper bound is definitely big enough. So lower boundary, upper boundary, and then what? Mean and standard deviation. So 2,400 and 108. Make sure you are labeling these things, not just writing down the numbers. And what do we get? 0.1772. So 17.72% probability that they will exceed the weight limit. All right. Let's look at the last one on this white page. A manufacturer of iPods purchases computer chips from a vendor. When a large shipment is received, a random sample of 200 computer chips is selected and each is inspected. If the sample proportion of defectives is more than 0.02, the entire shipment will be returned to the vendor. What is the approximate probability that the shipment will be returned if the true proportion of defectives in the shipment is 0.05? So this time, are we working with mu? No. Now we have P. True proportion would be P. So that's what they're telling me right here. Why don't they give me a standard deviation? This is something that we calculate. With means, they have to give us the population sample deviation, standard deviation, so that we can calculate the sample standard deviation. With proportions, you use the proportions to calculate the standard deviation. All right, so let's check our conditions first. First condition would be random. Do we get our random condition? Where does it say? Random sample of 200 computer chips. All right. Then 10%. What would this look like? 200 less than or equal to 10% of all computer chips, yes. And then our last condition, large counts. And what are we checking large counts for? Checking this for normality. Large counts helps us with normality. It's similar to central limit theorem. Except with large counts, we have to make sure that n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. As long as that is true, our sampling distribution will be approximately normal. So what do we multiply together for n times p? .05. Because remember, it said assume the true proportion is 0.05. What is 200 times 0.05? 10, exactly. So we meet that criteria. Barely, but we do. And then n times 1 minus p, so 200 times 1 minus 0.05. 190. Greater than or equal to 10, we are good there. So one of the things that I do want to point out because it came up when we were learning this and then when we tested over this. I need to see n times p, plug in the numbers, show me that it's bigger than 10. Over here, I need to see n times 1 minus p. I need to see the numbers that you're using here. So 200 times 0.95 or 200 times 1 minus 0.05 before you just get down to telling me how much it is. This number here, along with the n times p, should always add up to whatever your sample size is. So we can kind of shortcut or double check our number there, but I still need to see it with the numbers plugged in. All right. Where do I go from here? We've been asked to determine the probability that the shipment is going to be returned. What did we determine about the shape of this distribution? Normal. So I can go ahead and draw a normal curve. Right down the center is my mean, but this is a mean for proportions. What is our sample mean? What is p? 0.05. The mean of p hat is equal to p, which is equal to 0.05. So that's the first thing next to my n. What else do I need? I need the standard deviation. Go back and look at that yellow page and tell me how to calculate the standard deviation of p hat. Square root over n. Yes, p times 1 minus p over n. So the square root of 0.05 times 0.95 over 200. What do we get? $0.0154. Where's the threshold for it getting returned again? 0.02. Which side of the mean is that on? It's on the left. Which way am I going to shade, left or right? I'm shading to the right because we want to know the probability that it's going to be rejected, and if 2% or more of these chips are defective, then they're going to send the whole shipment back. Before we even get to the normal CDF, I already know that my answer is going to be bigger than what? It's going to be bigger than 50% because I have shaded more than half of that graph. It's a really good idea to kind of get into your head, like, what would I be expecting as a reasonable answer? Bigger than this, smaller than this, just trying to ballpark it when you are putting the lines and the shading on there. So that way, after you do your normal CDF, you can evaluate your answer. This gives you a chance to look at it and say, should I have done 1 minus, or do I have the right lower and upper boundaries that I put into my calculator? All right, so then from here, the probability that p is greater than 0.02 is equal to normal CDF, lower boundary of 0.02, upper boundary of something big. What's the biggest this could actually be if we're talking about proportions? 1, because we've got an area of 1 underneath the curve and we're looking at proportions here. So I'm going to put, I don't know, just something big. But if you use a 1 here, that would be sufficient. That would be large enough in this example. Lower boundary, upper boundary, and then mean 0.05. And the standard deviation of 0.0154. We end up getting what? 0.9743 is absolutely correct. Nicely done. There is one free response question that I would like to look at since we actually have time. If you want to come grab a whiteboard and a marker and an eraser, you're welcome to, or you can grab scratch paper and do this on scratch paper. Your question is up on the screen. A local radio station plays 40 rock and roll songs during each 4-hour show. The program director at the station needs to know the total amount of airtime for the 40 songs so that time can also be programmed during the show for news and advertisements. The distribution of the lengths of rock and roll songs in minutes is roughly symmetric with a mean length of 3.9 minutes and a standard deviation of 1.1 minutes. For part A, I want you to describe the sampling distribution of the sample mean song length for random samples of 40 rock and roll songs. And then for part B, if the program manager schedules 80 minutes of news and advertisements for the 4-hour show, 240 minutes, only 160 minutes are available for music. Approximately, what is the probability that the total amount of time needed to play 40 randomly selected rock and roll songs exceeds the available airtime? I'm going to give you guys, let's see if we can do this in 7 minutes. If I need to add a little bit of time on, I can.
So back here, I probably should have explained a little bit better. We calculate first the sample standard deviation, which is the population standard deviation divided by the square root of n. But then we were looking at collecting more than one, so then we had to multiply by n also. So the first thing was the sample standard deviation, and then just like with means, we can multiply the sample standard deviation by a constant to get a standard deviation for a larger group. There's more than one way that you can go about doing part B on this. That is one of the ways that you can calculate standard deviation for that. Did you have a question? Okay. No, that's okay. I just wanted to make sure I'm not missing anybody. So on part A, it says to describe the distribution. That's chapter 1 stuff, describing the distribution. What's the acronym that we use to describe a distribution? SOX. DUFS is for scatter plots. DUFS is for scatter plots. So that's when we have two variables that are both quantitative. So we need to describe the shape, outliers, center, and spread, the variability. What could we say about the shape? Approximately normal. Why? Greater than 30. 40 is greater than or equal to 30. That's the central limit theorem. So it is approximately normal. Outliers? Not really. Assumed no outliers. I'm not going to write it down because I barely have any room to write up here, but assumed no outliers here. When we're looking at averages, it's a lot harder to have those outliers when we're looking at sample averages. All right, then we need center. Which measure of center would we use here? What are the different measures of center? Median, mean, technically mode, but we never use mode. So would we use mean or median here? Mean. It said it was approximately symmetric at the beginning, so I know we have to use the mean. The only time we use the median is when we are skewed or have strong outliers. So the mean for the sampling distribution, it says the sample mean song lengths. So we're looking at the average of how many songs? The average of 40 songs, but we're looking at how many songs each time, according to this. Like when it talks about the average song length or the distribution of average song lengths. We're just looking at the average, like we're taking this whole group of 40 and we're averaging it out and we're saying typically it's about this long. So we're taking it down to the average song length for one song out of a sample of 40.
So the mean for X bar is going to be the mean for my population, which is what? 3.9 songs. And I brought that up to talk about when we're talking about average song length, because when we go to calculate the standard deviation, I don't want the total average song length for 40 songs. I want the average song length for one song, calculated based on this group of 40. So the standard deviation for X bar is going to be the standard deviation for the population divided by the square root of n. What was the population standard deviation? 1.1 divided by the square root of 40. That would be 0.174. And this should be minutes, not songs. I don't know why I wrote songs. Minutes. Standard deviation of 1.74 minutes. Part B, there's two different possible ways you could go about it. You can use what we just calculated in Part A for the mean and the standard deviation. And then we would look at their total and say, well, if they have a total of 160 minutes available for music and they're going to play 40 songs, each song needs to be about how long if it's going to fit in that 160 minutes. So you can do it that way. Or you can look at it as a total group. Thank you. So the way I would approach this problem is to say we have 160 minutes available for music. We're going to play 40 randomly selected songs. So 160 divided by 40 would give us what? 4. Each song needs to be 4 minutes or less to fit in the time, right? And so then we could do our normal curve. Right down the center, we have our mean of 3.9. This is normal with 3.9 and 0.174. We want the probability that these songs are 4 or more minutes, because that would put us over the time. Does that make sense? Okay. The other thing that you could do if you wanted to look at this total of 160, you would have to take the mean of 3.9 times 40, and you would have to take the standard deviation of 0.174 times 40, and then you could look at the total of 160. So that would be another way that you could approach Part B and still end up with the exact same probability. All right, tomorrow we're going to review confidence intervals and hopefully start touching on hypothesis tests.